Welcome to Chapter 8, wherein we will be looking a lot at right triangles and learning about trigonometry, which is, in my opinion, about the most important thing to carry with you out of geometry into future math. It remains important for forever. So it starts off in our booklet with an activity to basically prove that if we draw an altitude from the right angle corner of a right triangle, that we always end up splitting the right triangle into two smaller right triangles, both of which are similar to the original. So in this case, we have triangle ABD. So I'm going to mark these angles and give them a name. I'm just going to call this one alpha, and this one beta, just so they have a name. And we know that this last angle was 90. So my original triangle, those were its three angles, and then this smaller triangle, we have a 90 degrees because altitudes are perpendicular to the side that they meet, and we have this angle beta. Well, that means that by subtraction from 180, this one must be alpha. So now we have a similar triangle to our original. Same thing over here, we also have a 90-degree angle here with an angle alpha, so what's left over here must be beta. So we end up having three similar triangles, and then we get some interesting proportionality based on the kind of stuff we learned in Chapter 7 that we can look at here. So first thing we're going to look at is a topic called geometric mean. So mean you're probably familiar with. We say that mean is like average. So the way we're used to looking at mean is called the arithmetic mean. So arithmetic mean is where we take, if we have x and y, we're going to average them. So we're going to use a plus, I don't know why I put a 2 there. We're going to use a plus x plus y, and then we're going to divide that in half. So my operations here are addition and division. And if you remember arithmetic sequences, those are ones that count up by addition. So we went like 2, 5, 8, 11 is a sequence where we're adding at each step. So arithmetic goes with additive things like this arithmetic mean, which again, usually we've just called mean. But there's a second kind of mean that we can look at called the geometric mean. And if you remember again with sequences, if I had 2, 6, 18, 54, and so on, where each step is being accomplished by multiplication instead of addition, geometric is kind of a step up from arithmetic in our hierarchy of order of operations. So arithmetic is down here with addition and subtraction, and then geometric is a step up on our order of operations right here at multiplying and dividing. So instead of doing x plus y divided by 2, we're going to do x times y, and then instead of dividing by 2, we went from addition up to division. We're going to go from multiplication up to exponents. So we're not going to divide by 2, we're going to raise it to the 1/2 power, which is equivalent to saying the square root of x times y. So that's what we end up with geometric mean, and it has a lot of important properties with those three similar right triangles. So let's take a look at some of those. It says if the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar, as we just saw, to the original triangle and to each other. Given these, you can write similarity statements. We've just done a lot of that in the last chapter, but basically we're just matching up short to short and long to long. So if my original was A, B, well, that's weird. This doesn't match the order. D, B, C, that one matches. So this should be A, C, B. And then that one is, oh, that is ACB. Wait, what's going on? This one should be ADC. So this is the typo. So ADC, CDB, and ACB, And we just want to look in each of those, and so my shortest side of this one is AD, and my shortest side of the big triangle is AC. So here I would go ADC is similar to, and then over here my shortest side was AC, so that would be ACB. And then in the middle my short side was CD, so we would go CDB. So you know all about matching up similar or corresponding sides of similar figures, so we don't need to spend time on that. Given triangle DEF with right angle at vertex F, write similarity statements. So I'll let you go ahead and draw that one and do that one on your own. I don't think we need to spend more time on it. Okay, so notes sheet, we've got the geometric mean of two positive numbers. We'll call those A and B here, just arbitrarily. I called them X and Y before, but we're going to call the geometric mean here is going to be X. And it's going to be basically proportional such that A over X equals X over B. So this is a way of thinking of it in terms of a proportion, whereas before I said it was basically like A times B and the square root or 1/2 power of their product. But it ends up being the same thing. So if you cross multiply here and then square root the X, you end up with the same exact result. So we're going to find the geometric mean between 5 and 45. So thinking in terms of arithmetic mean, if I had 5 and I had 45, my arithmetic mean is exactly the midpoint of that. So I would go halfway between those to 25. And the key there is that I'm going plus 20 and plus 20. So we can think of this like a little 3-term arithmetic sequence. Now our goal here, what we're going to end up with, is starting from 5, going to 45. We want to find this point such that we multiply by the same number to go from 5 to there, and from there to 45. So doing this geometric mean accomplishes that, but I think that with this one we can see that we would multiply times 3 to get to 15, and then times 3 to get to 45. So that turns out to be the exact same as if we do 5 times 45, we would get 225, and the square root of 225 is 15. So we find that point, whether we think of it as multiplying by the same thing twice, which is kind of like making an exponential sequence, or by multiplying the two endpoints and square rooting them to find the thing in the middle. So a couple of different ways of visualizing, but we get the same results. So our geometric mean here was 15. 8 is the geometric mean between 6 and what? So again, two ways of thinking. I could say 6 to 8 is multiplying by 4/3. So if I multiply by 4/3 again, I would have 32/3. So that's going to be my answer. Then if I wanted to solve it the square root way, I would have said 6 to x to, no, sorry, we knew the middle term here. 6 to 8 to x would be 6x, and then the square root of that equals 8. So then I would need to square both sides to get rid of this square root. I would get 6x equals 64. And then I would take the 6 and divide it. We get x equals, and then we have 32/3 again. So same answer. Different way of arriving at it. That way will work in cases where the other way is a little tougher. Going from the first to third, so finding that geometric mean if you know the start and end point, can be fairly difficult to do the way I did here, because you just have to kind of recognize what the number is. And if it's a fraction, that becomes very difficult. So this square root way is also pretty important. When we have the first and second term and we're looking for the third one, I actually find this proportional method to be way easier than doing the square roots. All right, so geometric mean or altitude theorem. So this is going to give us relationships within our three similar right triangles based on geometric means. So it says the altitude drawn to the hypotenuse of a right triangle that separates it into two segments. That's the altitude we were talking about on the previous slide. So haven't really gained any knowledge there. So we're just talking about a right triangle. It's not very right, in which we're drawing this altitude, the one that splits the right angle. The length of the altitude is the geometric mean between the lengths of the two segments of the hypotenuse. So we kind of need a triangle. They say CD here, but we don't have a picture to reference. So let's call this A, B, C was the triangle, and then D, so CD is our altitude. So CD is the geometric mean of the two parts of the hypotenuse. So that would be here AD and DB. So that's our geometric mean is like this picture. So then the geometric mean leg theorem, so that's talking about the hypotenuse and the altitude. This one's talking about the hypotenuse and the legs. So it says the altitude drawn to the hypotenuse of a right triangle separates into two segments. Again, just this altitude, same thing. The length of a leg of the triangle is the geometric mean between the length of the hypotenuse and the segment of the hypotenuse adjacent to that leg. So, using our same triangle, CB is a leg and AC is a leg. And it's saying that those are the geometric mean between the length of the hypotenuse, so that would be AB in both cases, and the segment of the hypotenuse adjacent to that leg. So adjacent to CB would be BD, and adjacent to AC was AD. Now, I find that definition very hard to internalize, so I tend to just think of my three similar right triangles and set up this proportion by matching sides. So thinking about my big triangle, AB is the longest side, and CB is the shortest side. Then within this little triangle, CB becomes the hypotenuse, so it is now the longest side, so I match it up with AB. And within that small triangle, if I draw on it better, BD is the shortest side, so it matches up here on bottom with the short side. So all we're doing is writing a proportion of two similar triangles. We're just kind of coming up with a way to shortcut it using this geometric mean so that we don't have to redo that work every time. But for me, I find it easier just to look at the two similar triangles and rederive this rather than trying to memorize it. Up to you how you want to handle it. So we want to find x, y, and z. We know the hypotenuse, and we know the leg of this the short leg of this smallest triangle. So basically, my proportion is going to be 25 over y, because I'm going from hypotenuse to shortest side, is equal to the shortest side of this same triangle with the hypotenuse of this smallest triangle, which is y over 5. So the idea here is if we can recognize that as a geometric mean, we don't have to write this proportion. We can just go straight to y equals the square root of 25 times 5. I struggle with that, but if you can see that and are okay with it, then by all means, I would say do that. So then y is going to be the square root of 125, which we simplify as 5 square root of 5. Now we can do similar things for the rest. So we knew that the altitude is the geometric mean of 20 and 5. That to me is a really easy one because I know that from there to there is times 4. So if I wanted to go halfway, I would do times 2 times 2, and 10 would be the geometric mean of those two. because I multiply by 2, multiply by 2. So z equals 10. And then finally on this one, I have 25, and then the matching, or the leg closer to x is 20. So it's going to be the square root of 20 times 25. And that's going to give me, what would that be, 500? Yeah, 50 plus a 0, so 500 square root. So there's a 100 in there, so that means that's 10 square root of 5. So that would be x. So that's how we can use these theorems in order to, so that last one I actually did it. I did the right thing and shortcutted it without writing out the whole proportion. So these are just little shortcuts that can help us find all of these different pieces of these right triangles. All right, so then we have some practice on this. I'll look at 1 or 2 of them with you, and then hopefully you'll be good to do the rest. So first one, let me make my picture. Okay, first one, and I'm actually going to make it bigger. So view, page width, there we go. Okay, so we have, we're going to mark these things on the figure. So AD is 2, DB is 8. That means we know the hypotenuse, so we're probably using the leg version of the theorem, not the altitude version. And it says CD. Oh, I was absolutely wrong. We're finding CD, which is going to be the geometric mean of those 2 parts of the hypotenuse. So to get from 2 to 8, I need to multiply by 2 and then 2 again. So in this case, CD is going to be 4. So I could also have done that as, if you wanted to be more formal, the square root of 2 times 8, which is the square root of 16, which is 4. And you may say, when we do the square root of 16, isn't that plus or minus 4? And we don't have a negative root here because one of the conditions of our theorem was that all of these things are positive. And since it's geometry, we know we don't have negative lengths of things. But in order to kind of follow this whole process, we need to kind of have the understanding that 2, 4, and 8 are all required to be positive in this case. Okay, next thing we have AD is 3. DB is 6, so again we know the 2 halves of the hypotenuse, but this time we want AC. So we know that this one is the geometric mean of the closer leg and the total hypotenuse. So we're going to have 3 times 9, and we're going to take the square root of that. Well, 9 simplifies as a 3, so that's 3 square root of 3. And then we'll look at one more since it's on the page here. BC is 6, AD is 5, and we want to find DB. So we know that 6 is the geometric, let's see, 6 is the mean of this one and the entire hypotenuse, but we don't have that part here. So what would we do? I guess we would say that this is an x, and then we would need to have an addition. Like, we're going to have x in 2 places then. So that means that, so x is the closer leg, so x times 5 plus x is going to be equal to, so the square root of that is going to be equal to 6. Right? Sure. Yeah. Okay. Yep, that's going to be equal to 6. So we'll square both sides, which technically is not an operation we're normally allowed to do, but since we're only dealing with positive roots, it's okay. In theory, when we square both sides, we're introducing an additional answer because of that option of having a negative root when we take the square root. But we don't have to worry about that here because, again, we're eliminating all negatives as options. So in this case, we are allowed to do square root of both sides and get 36 here. And then if we multiply this out, we get x squared plus 5x minus 36 equals 0, because we bring the 36 to the left. And then we need factors that multiply to 36 and subtract to 5. So that would be 9 and 4. So I'm going to factor that as x plus 9 times x minus, I said 4, right? Yeah, x minus 4 equals 0. So my two theoretical solutions are x equals 4 and x equals negative 9. But since we've said negatives are completely disallowed here, that's the extraneous solution we added in, and our only solution is x equals 4. So that's a few examples, even one with the quadratic, so hopefully that helps get you set on what we're doing here. But basically, we're finding a middle piece by using a shorter piece and longer piece in these similar triangle proportions. So do some more practice on this and you'll get it down.